Welcome back to the third week of the course Cobotics Theory and Practice. In this week we will discuss on transformation matrix and robot kinematics. It will have 4 lectures. First will be on degrees of freedom, matrix representation and kinematic transformations. We will begin with translation matrix, and second lecture will have kinematic transformation. We will continue with rotation transformation, arbitrary axis rotation and Euler angles. Lecture 3 will comprise of robot frames, DH parameters, link transformation matrix and forward kinematics. Moving ahead to fourth lecture of this week, we will have discussion on forward kinematics of standard industrial cobots. So let us begin with the first lecture, that is degrees of freedom, matrix representation and kinematic transformation. We will start with translation matrix operator. The overview of this lecture is as follows. We will begin with degrees of freedom. We will discuss Grubler-Catchback criterion for calculating degrees of freedom. We will discuss on spatial description and transformation, transformation matrix, homogeneous transformation matrix, and we will finally end up with kinematic transformation, discussing with translation matrix operators. So let us begin with degrees of freedom. So yes, the degrees of freedom of a mechanical system is the number of independent parameters that define its configuration or state. Let us say if it is a robot, it has multiple degrees of freedom. Okay, it has first revolute joint here, it has second one which is here, okay, and the third one, let us say it is here. So we define each one of them, that is theta 1, theta 2 and theta 3, those are the revolute joint angles to finally define the end effector coordinates, that is the pose of the robot. Okay. So it needs to be defined all the 3 angles theta 1, theta 2 and theta 3 so as to fully define the state of the robot, that is defined by the end effector coordinate, that is where it is at xyz or it is at xyz roll pitch yaw. So complete information about its state is given by the 3 input states of its joint angle. So this robot will now have 3 degrees of freedom. So this is just an example giving you using a robot for any mechanism, any parallel, serial or any kind of mechanism, okay, or a machine, this is the same. Okay. So effectively total degrees of freedom is summation of all the degrees of freedom minus number of constraints. So number of independent constraints that can be put to a robot so as to fully constrain a robot. In terms of robots, let us say again similar robot, let us say it has 2 degrees of freedom and it has one link 1 and other link 2 with joint angle theta 1 and theta 2, finally defining the end effector coordinate. If I constrain this joint, end effector can still change its coordinate by just changing the second joint angle. If I again weld it up fully, second joint also, then end effector is fully constrained. So that means to constrain the end effector, you need to constrain all the joints. So number of independent constraints that you need to put so as to fully constrain the end effector or the fully define the pose of the robot. So this is what becomes the degrees of freedom of a particular machine or a robot or a mechanism. Okay. So now let us look at various degrees of freedom which could be there in any joint. Standard kinematic pair, it is known as, they are called as joint in case of robots. So if it is a revolute joint which is normally there in any of the robot joint in case of revolute jointed robot. So if it is a robot like this, so this may have a joint which is here, it has a joint which is here, okay, it has multiple joint which finally make it up. So these joints are normally revolute joint. So in this case, so any body with respect to a fixed frame can have maximum of 6 degrees of freedom. So, in this case, if it is having 1 degrees of freedom, that is just revolute joint about one of the axis, that means remaining 5 is fully constrained. Okay. So, all 5 constraints would include translation along this direction and this direction, and rotation along this, okay, and it also constrains the translation along vertical axis. So, altogether 5 degrees of freedom are constrained, one of them is left free about which this joint is defined. So, this is a revolute degree of freedom. Next one is a prismatic joint. This is quite common in case of robot again, or it is a plunger and barrel kind of system, or a hydraulic plunger if you have seen, or a typical syringe, they have such kind of joint. So, it is a prismatic joint. So, in this case the plunger can only go back and forth into the cylinder or out of the cylinder, right. So, it cannot rotate about any of its axis if it is shaped like this. So, it is again constrained by 5 degrees of freedom and 1 degree of freedom is left free. So, this is a prismatic joint. The third one here is a helical joint. So, this is rarely used in robot. So, if you rotate, you also transport in one of the direction, okay. You also translate in this direction. So, when I rotate, I also translate. That means they are not independent to each other, okay. So, that means if you rotate, you also translate. So, even though it looks like it has one revolute and one free translation direction, but it is not. So, it effectively leads you to 1 degree of freedom only, because 2 of them are linked, which appears like free, and others it is fully constrained. So, remaining 4 is fully constrained, 2 of them are linked, finally ending you to 1 degree of freedom only. Next is a cylindrical joint. This is very much similar to a revolute joint only, but in this case you can move along this vertical direction also. So, 2 are free and 4 is constrained. This is again, this is quite common universal joint. It is used quite commonly in robot passive joint, normally in case of parallel robots also, okay. So, this is having 2 degrees of freedom, rotational degree of freedom orthogonal to each other, that is free, and remaining degrees of freedom, 4 degrees of freedom are constrained. So, it is left with 2 DOF. This is known as universal joint. And the sixth one, that is the final one, is having 3 degree of freedom. It is known as spherical joint. So, it can have rotation along all the 3 orthogonal axes, and it cannot have translation in any of the directions. That means 3 translation is constrained and 3 is free, 3 rotation is free. So, altogether it has 3 degrees of freedom. So, these are standard kinematic pairs which are known as joints. Quite commonly 2 DOF, universal joint, prismatic joint and revolute joint is very much common in robotics. Next one is Grubler-Krachbak criterion for degrees of freedom calculation. Chebyshev-Grubler-Krachbak criterion, this is more common name to it. Krachbak gave a planar equation for that to find out the degrees of freedom based on the conditions like number of links that it has, number of kinematic pair it has, it can calculate. So, these are the 2 formulas. So, the derived form of Grubler-Krachbak criterion for calculating the degrees of freedom of any system is given by this and this. This one was given by Krachbak-Longback, that is only for planar, whereas the second one was an extension to this, which is given by Grubler later on, which is also applicable for spatial systems. So, that is for 3 dimensional and this is for 2D planar system, okay. So, it says n is equal to 3 times of r minus 1 minus 2p, and the second one is n is equal to 6 times of r minus 1 minus 5p, where r is number of rigid bodies or links in the system including the base of the robots. P is number of kinematic pair or joints in the system, and N, that is the output, is degree of freedom of the whole system. Let us look through one of the example. This is a 4-bar mechanism here. Okay. So, number of link including the ground is 4, 1, 2, 3, and the one which is connecting these two is a static link, which is not a moving link, but it is making these two points at a fixed distance. It is not allowing this distance to change. So, this is also a virtual link which is placed at the ground. So, effectively it is 4th link. So, total links are 4. Number of kinematic pair here is 4 revolute pair, you can see 1, 2, 3 and 4. Okay. So, it is a planar system. So, I will use the first formula. Okay. So, it says n is equal to 3 times of r minus 1 minus 2p. If I substitute r and p here, what I get is 1 degree of freedom. So, this mechanism is a single degree of freedom system. So, over here you see, can you apply the degree of freedom definition here? So, number of independent constraint needs to be defined in order to fully define the system, or number of independent constraint that I can put so as to fully constrain this system. So, let us just weld one of the joints. So, if I weld this one, I have put a constraint here. That means now if I freeze this up, what will happen? This point will be frozen. So, if this point is frozen, that means overall system is now a triangle. So, this cannot move, this cannot move. Okay. That means remaining 2 is making it a triangle which is a stiff structure and it cannot deform. None of the joints can further move. So, that means whole of this structure is now fully constrained. This mechanism can no longer move. That means just by fixing one of the joint, whole of the mechanism get fixed. Okay. So, that means it has 1 degree of freedom. Okay. Let us extend this example by this one. Over here I have just added one additional link here with 1 revolute joint and 2 revolute joint, and this is the additional link here. So, in this case R, that is number of links, become equal to 5, 1, 2, 3, 4 and 5. Number of joints here is 6. Okay. That is kinematic pair is 6. If I put them in planar equation, it gives me 0. Is it really 0 here? If this mechanism, you all know, it can at least move like this. All the links will move parallelly and they will move like this. Okay. So, yes, it has some degree of freedom, that is quite obvious, but yes, using this equation it comes to 0 here. How is it possible? Actually, you see link 3 over here is a redundant link. It has no role to play, and these two joints also. This is just supporting it. Let us say there is a huge load from here. Yes, it can help you to take up that load in order to prevent it from sagging, something like this. Okay. But definitely it does not have any role in creating the motion or maybe creating a new type of motion anywhere on the system. Okay. So, that means this is a redundant link which is there only to support the system. This should be removed before you calculate the degree of freedom of the system. Okay. Otherwise, this type of results is quite possible. Okay. So, link 3 is a redundant link and it should be removed before calculating the degree of freedom. So, yes, in case of serial system, as in case of industrial robots, they are just like arm. In that case, you will find it gives you degree of freedom exactly equal to number of joints. Okay. That is in case of any serial chain system like this, okay, that is for any robot, okay. So yes, let us move ahead with a special description and transformation. What is that? Before we actually move in, let us formalize standard symbols and notations that I will be using throughout my lecture from now and on. So matrices will be represented using bold capital, vectors or any point represented in matrix form are represented using lowercase, boldface, Latin or Greek letter like this, scalar like this, any frame or any position in space will be denoted using capital letter, italic. Unit vectors will be represented using a cap on the top and small letters, italic. Vector joining the two frames like O and F over here is given as a vector with a arrow mark on the top. Standard text will be like this, and any subscripts that are used for indexing will be like this. Example is acceleration due to gravity, and the three dimensional vector is this, that is a G and a Z, okay. Both are same, but one of them is a vector, other one is the magnitude of G, that is a scalar quantity, okay. So mind it, this is very important because you should be conversant with these symbols and notations in order to follow my lectures, okay. Let us start representing a point in a space. This is a point space. Here I would mean a Cartesian space where you have x, y and z, three orthogonal axes, they are 90° to each other, okay. Before we begin, we are formalizing this. It is not an oblique axis, it is not a cylindrical coordinate system or a spherical coordinate system, it is a Cartesian coordinate system, okay. And any point here is given by three coordinates ax, by and cz. So these can be written as a position vector. So any point P, this is the position vector. So this is your P that comes here. It may be written as ax I, by j and cz k. So they are I, j and k are three unit vectors along these orthogonal axes, okay. So ax, by and cz are basically the projection of this position vector along x, y and z, okay. So this is a well known fact, by now you already know this. Next, it can be represented just as a coordinate, as in bracket you can write ax comma by comma cz. This is another very popular format, but in case of robots and robotics we will be using something like this. It will be denoted using a vector p, okay, given as ax, by and cz. W is 1 in case of robotics. So effectively it will be ax, by, cz 1. So this is a 4 cross 1 matrix with which a point in a space will be denoted, okay. Now representing a frame over here, this frame is coinciding with the origin frame, but yes, you see it is little bit rotated. So it is again given by three orthogonal vectors which are mutually perpendicular to each other, normal n, okay, this is n, this is O, orientation and approach vector. Three orthogonal vectors are these nx, ny, nz, ox, oy, oz, ax, ay, az are their orthogonal projections along x, y and z, okay. So nx means projection of n along x, n along y, n along z. Similarly for O, it is O along x, O along y, O along z. For approach A along x, A along y, A along z. So these are the projection of NOA along 3 orthogonal directions. So, that finally gives me 9 elements to fully define this. So, effectively in matrix form it can be written as a frame over here, as because it is a matrix here 3 cross 3, it is in bold capital. So, you see it is nx, ny, nz, ox, oy, oz, ax, ay, az. So, these 9 elements finally would form the matrix and finally the frame. Okay. So, now the frame in a fixed frames, that means location of this frame in the fixed frame. Location here would also include the orientation. Basically NOA will finally give you the orientation of frame F with respect to frame O, because it has components along x, y and z for all the 3 vectors, unit vectors, which were assigned to the frame, that is N, O and A. Okay. Here you see there is an additional column here, that is Px, Py and Pz and 1. Okay, that is in standard robotics format. So, it is Px, Py, Pz. What is that? P is the vector, position vector from O to F, it gives you the location of F. So, P along x, P along y, P along z are the projections of P along x, y and z axes. Okay. So, that is finally gives you the position of the frame, position of frame with respect to origin O. Okay. So, this is the complete representation of the frame in space, that tells you the orientation using these 3 columns and position using the last column, which is here. Okay. So, this finally tells you the position and orientation of the frame in space. Okay. Over here you saw it is Px, Py, Pz, that is the translation along x, along y and along z direction. We will finally discuss more about this later on in this lecture. Representing a rigid body would now require the frame to be put on a rigid body. A frame once put to the body, that is enough to define the position and orientation of the whole of the rigid body. That means, if you define the location and orientation of the frame, you have fully defined the rigid body also, because this body is not deformable. So, you see you have F of the object, that is object frame, now would become the same as that of frame's location. Okay. This frame is fixed to this rigid body somewhere over here. Okay. So, whatever is the position and orientation of this frame, that becomes the position and orientation of this whole rigid body in space. So, this is how we will define the whole of the rigid body using the frame F. This is represented using a point on the body. This frame is put anywhere on the as a point on that rigid body. Okay. It can be any point on the body. Position will differ, but definitely the orientation of whole of the frame will not change. If this location of this point changes, position will change, but definitely the orientation will remain the same. Now, let us come to homogeneous transformation matrix, translation matrix and rotation matrix operators. So, to begin with, we will start with transformation matrix. A transformation matrix essentially is an operator which is given by 4 cross 4 matrix, which is when applied to a position vector represented as a column vector. You have seen a point, a position is given by Px, Py, Pz1. It makes some movement in space. Movement can be translation, it can be rotation. In case of robotics, these two movements are possible. Okay. So, it can be a pure translation, it can be a pure rotation about an axis, okay, or it can be combined translation and rotations. It can be multiple rotations also. So, a general homogeneous transformation matrix operator will be given as 4 cross 4 matrix, which includes rotation transformation matrix over here and translation transformation matrix over here. So, we will understand very much in detail these elements one by one. So, what this does basically, R3 cross 3 is a sub matrix that is responsible for rotation operation, and T3 cross 1, that is the last column 3 elements, performs the translation operation in 3-dimensional Cartesian space. So, overall this transformation matrix is to be applied to a point so as to transform that point. So, that is the reason why it is known as transformation matrix. Okay. So, this homogeneous transformation matrix can now represent all the transformation as a matrix multiplication. So, you have to apply this transformation to a point to get to a new position or a pose, if it changes both the position as well as orientation. Okay. So, it is a multiplication over here. It captures composite, that is the translation as well as rotation transformation conveniently. A single matrix can have both. It can do transformation that includes rotation as well as translation operation. It can change the reference frame, not just a position vector, it can also change the reference frame of the object. Okay. It can displace a vector or a frame. A vector can also be displaced. It can represent the rigid body configuration. So, you have seen a homogeneous transformation matrix could now define the orientation and the position using this. You have seen it earlier here. So, it is much easier to calculate inverse of a square matrix. Now that it is a 4 cross 4 square matrix, it becomes quite convenient to take inverse transformation also. We will discuss very much in detail all these. Okay. So, now let us talk about translation matrix operator. Okay. How it happens? You see, this is the original location of this point in frame O. This is the position vector which tells you the position of point P in the frame O. Okay. And NOA gives you the orientation. We are not talking about that. So, I just want to translate this point from location P to P dash. So, pure translation matrix operator is given as this, where you saw the last column 3 element is the translation, that is what we are desiring here. This operator, when applied to the point P, you get the translated point P dash. When you multiply this transformation operator to this point P, what you get? This is, there is no rotation, there is unit matrix in the 3 cross 3 rotation space of this transformation matrix. Okay. There is only elements present in the translation part of it, that is 3 cross 1 part of it, that is last column here. So, this when multiplied with this, you see the location of this point has changed from projections. Essentially initially it has is Px, Py and Pz, that later it became Px plus D, Py plus dy and Pz plus dz. So, these are the individual translations along each axis it has happened. So, and those were put over here dx, dy and dz. So, whatever the element that goes here, the value that comes here is the value that is added along each orthogonal axis. So, this is how this is capable to transform your point from P to P dash. This is known as a translation matrix operator. Okay. So, in the next class we will follow this up and we will discuss on kinematic transformation. We will extend it to rotation matrix operator also. We will see what is arbitrary axis rotation, how to do that, and we will also discuss on Euler angle systems. That is all for this lecture. Thanks a lot.